Integration by parts, level 1. Integration is not as straightforward as differentiation. There are no rules that absolutely guarantee obtaining an indefinite integral of a function. In the following videos, we will learn various integration techniques to help us find indefinite integrals of more complicated functions. Back in Calculus 1, we learned our first integration technique, specifically the substitution rule. Recall that every differentiation rule has a corresponding integration rule. For example, the substitution rule for integration corresponds to the chain rule for differentiation. Likewise, the rule that corresponds to the product rule for differentiation is called the rule for integration by parts. If we take the product rule and rewrite it using the notation for indefinite integrals, we would have the following expression. Remember, according to the fundamental theorem of calculus, differentiation and integration are inverse processes. So we can rewrite the product rule as follows. If we were to take the integral of the resulting expression of the product rule, we will obtain back the original function formed by the product of f of x and g of x. Again, because the fundamental theorem of calculus tells us that differentiation and integration are inverse processes. So this expression is the product rule written by using indefinite integral notation. Now here what we do is distribute the integral and dx operator, and we end up with the following expression. Finally, we solve for the integral of one of the products. In this case, I will solve for the expression all the way in the left-hand side. So rearranging the expression results in the following formula. The integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x times f prime of x dx. This formula is called the formula for integration by parts, and you can easily derive it by starting with the product rule and taking the integral of both sides and rearranging the equation. So there is no need to memorize this equation. An alternative way of writing this formula is by carrying out the following substitutions. If we let u equal f of x and v equal g of x, then the differentials of the functions are du equals f prime of x dx and dv equals g prime of x dx, respectively. Substituting these expressions, we have an alternative form of the integration by parts formula. Specifically, the integral of u dv is equal to uv minus the integral of v du. Alright, now that you know the integration by parts formula, when and how do you use it? First of all, when do you use it? Usually when you encounter an integral of a product of functions, such as the integral x times cosine of x dx. Notice that we have a product of two functions, specifically x and cosine of x. This is a perfect candidate for integration by parts. Alright, now let's find the integral by using the integration by parts formula. We will first solve it by using the first version of the formula. In order to use and apply this formula to our problem, we need to make a decision and determine which of the two functions will f of x equal to and which one will g prime of x equal to. This is an important decision. The main goal in using integration by parts is to obtain a simpler integral than the one we started with. Let's go over the correct decision. The simplest integral is obtained if we let f of x equal to x and let g prime of x equal to cosine of x. By making this decision, it turns out that f prime of x after taking a derivative of f of x will be equal to 1, and g of x is equal to sine of x after taking the integral of g prime of x. Remember, taking the integral of a derivative leads you to the original function g of x. Now we substitute each expression into the integration by parts formula. So we have that f of x times g of x becomes x times sine of x, and the integral of g of x times f prime of x becomes the integral of sine of x times 1. Here the integral of sine of x is just equal to negative cosine of x, plus the constant. Remember, we are working with an indefinite integral, and we need to include the constant. So the final answer is x times sine of x plus cosine of x plus c. Let's go back to the first step and see what happens when we make the wrong decision when determining our f of x and g prime of x. If we let f of x be equal to cosine of x and g prime of x be equal to x, then our f prime of x will be equal to negative sine of x after taking the derivative of f of x, and our g of x will be equal to x squared over 2 after taking the integral of g prime of x. Now, the problem arises when we substitute these expressions into the integration by parts formula. Doing that, we have the following expression. The integral of x times cosine of x dx is going to be equal to cosine of x times x squared over 2 minus the integral of negative x squared over 2 times sine of x dx. Notice that we actually ended up with a slightly more complicated integral than the one we started with. This is a telltale sign that you assigned your f of x and g prime of x functions wrong. The main point is to obtain a simpler integral. At this point, you should start over and switch the corresponding functions. A tip to avoid starting over is by mentally taking the derivative of your assigned f of x function and taking the integral of your assigned g prime of x function, and check to see if those functions become simpler. In this case, the function becomes simpler if we take the derivative of x, as opposed to taking the integral, which yielded a higher degree power function. In this case, x squared over 2. It's much easier to work with the function 1 than with the function x squared over 2. Before we end the video, let's solve the same integral using the alternative form of the integration by parts formula. Generally, this is the form that most college classes teach. In my opinion, using the first form of the integration by parts formula is the way to go. Nevertheless, some students like this second form because it is easier to remember for those students that like to memorize their way through math classes, which I personally don't recommend. Okay, the first step in using the second form of the integration by parts formula is to make a decision and assign a function for u and a function for dv. So we let u equals x, and we let dv to be equal to cosine of x dx. Notice that when we assign dv, we are also assigning the differential dx. So keep that in mind and make sure you include it in your substitution. Now we take the derivative of u with respect to x and solve for du by multiplying both sides of the expression by the differential dx. So we have that du is equal to dx. Next, we take the integral of dv, so we obtain v, which is equal to sine of x. Now we substitute u, v, du, and dv into the second form of the integration by parts formula. uv becomes x times sine of x, and v du becomes sine of x times dx. This is the same expression that we obtained by using the first formula. So taking the integral of sine of x and simplifying, we obtain a final answer of x times sine of x plus cosine of x plus c. It's really up to you which form you want to use. Personally, the first formula is a lot easier to work with, but the second might be easier to remember. Okay, in our next video we will go over more examples involving integration by parts.
Integration by parts, level 2. Alright, we're going to dive in and work on various examples. Recall that integration by parts is particularly useful for integrands involving products of algebraic and transcendental functions, such as logarithms, exponential functions, and trigonometric functions. Let's try the first problem. Find the integral of x times e to the x dx. Alright, we first need to notice that the integrand contains a product of two functions, specifically x and e to the x. This is a perfect candidate to use integration by parts to find the integral. Let's use the first form of the integration by parts formula. Remember, the first step is to make a choice and determine which of the two functions will f of x equal and which one will g prime of x equal. This is a critical step when applying the integration by parts formula. Keep in mind that you want your f of x function to be a function whose derivative, f prime of x, becomes much simpler than the original f of x function. In the same manner, you want your g prime of x function to be relatively easy to integrate. Following these steps, we have that f of x will be represented by x, because when we take its derivative, we end up with a simpler function, specifically the constant 1. Likewise, we let g prime of x be equal to e to the x. Now we need to take the derivative of f of x, so the derivative of x is just equal to 1. Next, we need to integrate g prime of x to obtain our g of x. Integrating e to the x results in the same function e to the x. Now that we have our four functions, f of x, f prime of x, g of x, and g prime of x, we substitute them into the integration by parts formula, as follows. Finally, we take the integral of e to the x, which is equal to e to the x plus a constant. So the final answer is equal to x times e to the x minus e to the x plus c. Alright, now let's work on the same example, but this time, let's use the second form of the integration by parts formula. This is usually taught in a typical college level calculus course. The first step is the same. We need to decide what function u will equal to and what function will dv equal to. Remember, you want u to be a function that becomes simpler when you take its derivative, and let dv be a function for which you can easily find its integral. With that said, we let u equal x, and we let dv equal e to the x dx. Make sure you include the differential dx when selecting your dv. This is an important detail. So now we take the derivative of u with respect to x and solve for the differential du. Doing that, we obtain that du is equal to dx. To obtain v, we take the integral of dv, or in this case, the integral of e to the x dx. Doing that, we get that v is equal to e to the x. Now that we have u, du, v, and dv, we substitute them into the integration by parts formula, as follows. Then we find the integral of e to the x. And doing that, we see that the final answer is equal to x times e to the x minus e to the x plus c. Alright, from this point on, I will use the second form of the integration by parts formula, specifically the u dv form, since it's the common formula that many college classes teach. Personally, I like using the first form, but you should use a form that is easier for you. At times, you might have to rewrite the functions in the integrand in order to apply the integration by parts formula, like in the following example. Find the integral of the natural log of x over x squared dx. Notice that we don't have a product of two functions. We actually have a quotient, but we can actually rewrite the function in the denominator by using a particular exponent rule. We can rewrite the rational function 1 over x squared as x raised to the power of negative 2. And now this integral can be rewritten as x to the negative 2 times the natural logarithm of x. Notice that we actually have a product of two functions. So now we can go ahead and apply the integration by parts technique to find the indefinite integral. So the first step is to assign a function for u and one for dv. Remember, we want u to be a function that becomes simpler when we differentiate it, and we want dv to be a function that can be readily integrated. If we assign u to be equal to x to the negative 2 and take the derivative, notice that we actually end up with a higher power rational function. Likewise, if we assign the natural log of x as our dv, we would have to take the integral of the natural logarithm, which at this point we have no idea how to find. So these particular choices of u and dv will not work. Let's reverse them and let u equal to the natural log of x and dv equal to x to the power of negative 2. Having assigned u, we take the derivative with respect to x, which is equal to 1 over x. Then we solve for the differential du and obtain 1 over x dx, or written another way as x to the negative 1 dx. Likewise, having assigned dv, we integrate it and obtain v, which is equal to negative x to the negative 1. Now that we have all the required functions, we substitute them into the integration by parts formula. Doing that, we have the following expression. The natural log of x times negative x to the negative 1 minus the integral of negative x to the negative 1 times x to the negative 1 dx. Simplifying the expressions, we obtain the following. And taking the integral of x to the negative 2, we obtain negative x to the negative 1 plus c. And finally, we simplify the expression and obtain the final integral of the natural log of x over x squared to be equal to negative the natural log of x over x minus 1 over x plus c. Okay, recall that we had no idea what the integral of the natural log of x was equal to. Well, that is about to change. We can actually use integration by parts to find the integral of this function. Let's try the following example. Find the integral of the natural log of x dx. Notice that we don't have a product of two functions. We only have one function, the natural log of x. But looks can be deceiving. We actually have two functions, the natural log of x and the constant function 1. So we assign u to be equal to the natural log of x and dv equal to 1 dx, or more simply as dx. So taking the derivative of u with respect to x and solving for du, we obtain 1 over x dx, or written another way as x to the negative 1 dx. And taking the integral of dv, we obtain v, which is equal to just x. Substituting these functions into the integration by parts formula, we obtain the following. And finally, taking the integral of dx, we obtain the final integral of the natural log of x to be equal to x times the natural log of x minus x plus c. This example illustrates that we can actually use integration by parts to find the integral of a single function. It's just a matter of spotting and creating a second function. In this case, it was the constant function 1 dx. Alright, in our next video we will find more complicated integrals that require you to repeatedly apply the integration by parts formula. Integration by parts, level 3. Alright, we're going to continue covering integration by parts. This time around, we will go over problems that require multiple applications of the integration by parts formula, and those that generate a constant multiple of the integral. Let's try the former type of problems first. Find the integral of x squared times cosine of x dx. Okay, This time around, we actually have a product of two functions, x squared and cosine of x. Like always, we need to assign our u and dv. The best choice occurs when we let u equal to x squared because this function becomes simpler when we take its derivative. So taking the derivative of u with respect to x, we obtain 2x, which is 1 power less than the original function, and as a result, a much simpler function. Next, we assign dv equal to cosine of x dx. Taking the integral of cosine of x, we obtain sine of x. Now that we have all the required functions, we use the integration by parts formula and substitute them. Doing that, we have that the integral of x squared times cosine of x is going to be equal to x squared times sine of x minus the integral of sine of x times 2x dx. Now notice that the integral of sine of x times 2x requires an additional application of the integration by parts formula. What we're going to do is to carry out a substitution and let the variable I equal this integral. That requires an additional application of the integration by parts formula. It's important not to lose track of the original integral we are looking for. So making the substitution, we have the following expression. Now putting that aside and focusing on this integral, we carry out the familiar steps and apply the integration by parts formula once more. Same ideas apply. Make u equal to a function that becomes simpler when differentiated. So we let it equal to x. In the same manner, we let dv equal to sine of x. So taking the integral of sine of x gives us negative cosine of x. Substituting these expressions into the integration by parts formula, we have the following. The integral of x times sine of x dx equals negative x times cosine of x minus the integral of negative cosine of x dx. We factor out the negative sign and simplify. And finally, taking the integral of cosine of x, we have that the integral of x times sine of x dx is equal to negative x times cosine of x plus sine of x plus c. Now, let's go back to the original integral that we are trying to solve and substitute I with these results that we just obtained. And then we simplify. Doing that, we obtain the following. Notice that we ended up with twice the constant here. Keep in mind that if you take a constant and double it, you still obtain a constant. So we can replace 2c with another constant. So after all that, it turns out that the final integral of x squared times cosine of x dx is equal to x squared times sine of x plus 2x times cosine of x minus 2 times sine of x plus c1, where c1 is just equal to twice the original constant. A word of caution. When making repeated applications of the integration by parts formula, you need to be careful not to interchange the substitutions in successive applications. For example, in this problem, we decided to let u equal to x and dv equal to sine of x. If in the second application we decided to switch the substitutions, with u being equal to sine of x and dv equal to x, we would obtain the following. The integral of x times sine of x dx would be equal to sine of x times 1/2 x squared minus the integral of 1/2 x squared times cosine of x dx. And I will be represented by x squared times sine of x over 2 minus the integral of x squared cosine of x over 2 dx. And substituting this expression to the original integral, we would obtain x squared times sine of x minus x squared times sine of x plus the integral of x squared times cosine of x dx. At this point, notice that by switching the second substitutions, we undo the previous integration and return to the original integral. So be careful when you repeatedly apply the integration by parts formula. Repeated use of the integration by parts formula seems pretty tedious at times. There is actually a little shortcut that can save you some time. It is often referred to as the tabular method. This method is best suited for integrals of the form x to the n times sine of a times x dx, or x to the n times cosine of a times x dx, or x to the n times e to the power of a times x dx. Let's use the tabular method to find the integral of the following problem. Find the integral of x squared times sine of pi times x dx. The first step is to set up a table with two columns. The first column will contain u and its derivatives, and the second column will contain dv and its integrals, or antiderivatives. Next, we select our u and dv for this integral. We set u equal to x squared. Now, the next step is to repeatedly take derivatives until we obtain 0. Doing that yields the following functions. Next, we take our dv and repeatedly take integrals to match the number of rows that were generated from the differentiation step. In this case, we take 4 integrals, one after the other. Doing that yields the following functions. Next, it's just a matter of pairing up the functions. So we take the function from column 1 and multiply it diagonally to the right by the function on the second column and second row. Next, we multiply the function in the first column and second row with the function in the second column and third row. and we repeat this pattern until we reach the function in the second column and last row. Next, we alternate the signs going down the middle between both columns for each row, as follows: positive, negative, positive, and include them when we multiply the diagonal entries. So in the first product would be a positive times a negative, which results in a negative expression. In the second product, we have a positive times a negative, which results in a positive expression. And finally, the last product, we have a positive times a positive, which results in a positive expression. Once all of this has been taken care of, we essentially have our answer. The integral of x squared times sine of pi times x dx will be equal to negative x squared times 1 over pi times cosine of pi times x plus 2x times 1 over pi squared times sine of pi times x plus 2 times 1 over pi cubed times cosine of pi times x plus c. Alright, in our next video we will go over an example that generates a constant multiple of the original integral and use the integration by parts formula along with the tabular method to find its integral. Integration by parts, level 4. Alright, the final type of integrals that makes use of integration by parts occurs when we encounter integrals like the ones in the previous video. The only difference is that we need to keep an eye for the appearance of a constant multiple of the original integral. Let's illustrate this idea with an example. Find the integral of e to the x times sine of x dx. Alright, like always, first step is to select u and dv. Notice that in this example, both functions are easily differentiable, or have a simple integral. So in this particular example, the choice of u and dv is irrelevant. Let's make u equal to e to the x and dv equal to sine of x. So we take the derivative of u and solve for du and obtain the following. Next, we take the integral of sine of x and obtain the following function. Substituting the four functions into the integration by parts formula and simplifying, we obtain the following. The integral of e to the x times sine of x dx is equal to negative e to the x times cosine of x plus the integral of e to the x times cosine of x dx. We see that we have another integral that contains a product of two functions, so we let I equal this second integral, and we apply the integration by parts formula once more. We set u equal to e to the x and dv equal to cosine of x. Taking the derivative and solving for du, we obtain the following. And taking the integral of dv, we obtain the following. Substituting the expressions into the integration by parts formula and simplifying, we have that the integral of e to the x times cosine of x dx is equal to e to the x times sine of x minus the integral of e to the x times sine of x dx. So now we substitute this result back to the original equation and simplify it to obtain the following. The integral of e to the x times sine of x dx is equal to negative e to the x times cosine of x plus e to the x times sine of x minus the integral of e to the x times sine of x dx. At first glance, it seems that we're going nowhere with this integral, but looking closely at the equation, we can actually add the integral of e to the x times sine of x to both sides of the equation. This is analogous to the way you solved a linear equation such as x equals 3 minus x, where you need to add x to both sides of the equation and then solve for x. We are essentially doing the same here. The only difference is that we are adding integrals. So keep in mind that you can treat integrals as algebraic expressions. So doing that, we obtain 2 times the integral of e to the x sine of x dx is equal to negative e to the x times cosine of x plus e to the x sine of x. And now we factor out an e to the x on the right side of the equation, and then we solve for the integral that we originally were looking for by dividing by 2 on both sides of the equation. And finally, adding the constant. We see that the final answer is equal to 1/2 times e to the x times the quantity negative cosine of x plus sine of x plus c. Since this integral requires the use of multiple integration by parts, we can also use the tabular method to find the integral. But we need to pay close attention and spot the constant multiple of the original integral. Let's illustrate how this is done. We first need to create 2 columns and select our u for the first column and our dv for the second column. Next, we repeatedly take the derivative of the function on the first column and take the integral of the function in the second column. Notice that we are not going to end up with 0, no matter how many times we take the derivative. So we need to spot a constant multiple of the original integral by multiplying the function in a common row. In this case, we spot the e to the x and sine of x terms. So this is where we stop taking derivatives and integrals and write out our equation. Make sure you take into account the alternating signs when multiplying expressions from the first column diagonally with the expression in the second column. Once we write it out, we collect like terms and solve for the original integral and add the constant. So now you have an additional version of the integration by parts formula. You can either use the first version or the second version of the integration by parts formula, or use the tabular method as long as you know how to use it. Using the formulas is better suited when you need to apply integration by parts only once, and the tabular method is useful when you need to use integration by parts multiple times. Alright, in our next video, we will practice finding definite integrals that require the use of the integration by parts formula. Integration by parts, level 5. Alright, in this 5th video, we are essentially going to go over 3 different examples, demonstrating all the techniques learned from the previous 4 videos. The only difference is that we are going to work with definite integrals, as opposed to indefinite integrals, which were emphasized in the previous 4 videos. Okay, before we dive in, let's combine the formula for integration by parts with part 2 of the fundamental theorem of calculus. So evaluating both sides of the first form of the integration by parts formula from a to b, and assuming that f prime and g prime are continuous, we go ahead and combine it with the second part of the fundamental theorem of calculus. Doing that, we obtain the following formula to evaluate definite integrals while using the integration by parts formula. The integral from a to b of f of x times g prime of x dx is equal to f of x times g of x evaluated from a to b minus the integral from a to b of g of x times f prime of x dx, or written in another form as the integral from a to b of u dv is equal to u times v evaluated from a to b minus the integral from a to b of v du. It's essentially the same idea. We find the integral or antiderivative of a function, and then we evaluate it using the limits of integration. Alright, let's try the first definite integral. Evaluate the integral from 0 to pi of x times sine of 3x dx. Okay, we notice that we have a product of 2 functions, so this integral is a perfect candidate to use integration by parts to find its integral. We first need to select our u and dv functions. In this case, we set u equal to x and dv equal to sine of 3x dx. Like always, we want our u to be a function that is easily differentiable, and at the same time, a much simpler function. Likewise, our dv should be a function whose integral is easily found. So taking the derivative of u with respect to x, we obtain 1, and solving for du, we obtain the following. Next, we take the integral of dv to find v. So the integral of sine of 3x dx is equal to negative 1/3 times cosine of 3x. Having obtained all of our required functions, we substitute them into the integration by parts formula. So doing that yields the following. Next, we simplify the expression in the first term, and factor out negative 1/3 from the integral on the right. Next, we find the integral of cosine of 3x, and obtain 1/3 times sine of 3x. Next, we simplify both terms and evaluate it from 0 to pi. Substituting the limits of integration, we have the following. We can simplify the terms of the left bracket by noticing that cosine of 3 pi is equivalent to cosine of pi, which is equal to negative 1. In the same manner, sine of 3 pi is equivalent to sine of pi, which reduces to 0. The terms in the right bracket reduces to 0 because 0 times any number is equal to 0, and sine of 3 times 0 is equivalent to sine of 0, which simplifies to 0. Simplifying the expression, we have that the final answer is equal to pi over 3. Alright, let's try the next one. Evaluate the integral from 0 to 1 of x times 5 to the power of x dx. Once again, we have an integral that contains a product of 2 functions, so we use the integration by parts to find its integral. We are going to let u equal x and dv equal to 5 raised to the power of x. Having done that, we take the derivative of u with respect to x and obtain the following. Then we solve for du. Next, we take the integral of 5 to the power of x dx, and obtain 5 to the power of x over the natural log of 5. Now that we have all the required functions, we substitute them into the integration by parts formula as follows. We simplify the left term, then we factor out 1 over the natural log of 5 from the integral, and then we find yet again the integral of 5 to the power of x dx, which is equal to 5 to the power of x over the natural log of 5. Simplifying the expression, we obtain the following. And now we evaluate it from 0 to 1. So doing that, we obtain the following expressions. The terms in the left bracket simplifies as follows. And the terms in the right bracket simplifies as follows. Remember, any number raised to the power of 0 is equal to 1. Finally, we add like terms and simplify. The final expression of the integral is equal to 5 over the natural log of 5 minus 4 over the natural log of 5 squared. Alright, let's try the final integral. Evaluate the integral from 0 to 1 of the quantity x squared plus 1 times e to the negative x dx. Alright, this integral will require multiple applications of the integration by parts formula, mainly because of the e to the negative x term and the second order polynomial. So we will use the tabular method for this one. So we create two columns. In one column, we will list u and its derivatives, and in the second column, we will list dv and its integrals, or antiderivatives. So we are going to let u equal x squared plus 1, and continuously take its derivative until it reduces to 0, as follows. In the same manner, we will successively find the integral of e to the negative x until we match the number of rows from the differentiation step. So doing that, we have the following. Finally, it's just a matter of pairing up the terms and multiplying diagonally down to the right. Make sure you take into consideration the alternating signs. They are always positive, negative, and repeats in that order. Include them as a third term that has to be multiplied along with the derivative and the integral functions. So you have a total of 3 terms that have to be multiplied by each other. Once we take the signs into consideration, we have the following. Next, we factor out a negative e to the negative x term and obtain the following. Now we evaluate it from 0 to 1. The terms in the left bracket signify as follows, and the terms in the right bracket signifies as follows. So the definite integral is equal to negative 6 times e to the negative 1 plus 3, or written in another form as negative 6 over e plus 3, and yet in another form as the quantity negative 6 plus 3e over e. Alright, in our next and final video on integration by parts, we will go over examples that require the application of multiple integration techniques. Integration by parts, level 6. Alright, we're going to jump straight into some examples. Let's try some slightly more challenging problems. The next 2 problems will require the use of multiple integration techniques, specifically integration by parts and u substitution. Let's give it a shot. Evaluate the integral from 0 to 1 of r cubed over the square root of 4 plus r squared dr. Notice that this problem seems like a perfect candidate for u substitution, since we have similar expressions in the numerator and denominator. It seems natural to let u equal 4 plus r squared. If we do that and take the derivative of u with respect to r, we obtain 2r. Notice that we actually have r cubed and not r to the power of 1. It seems that u substitution has failed. Let's think through this one a bit more. We know that we need the numerator to be equal to r, but we have r cubed in its place. What can we do to fix this? One idea is to break it apart into r squared times r, like this. Now we actually have a product of 2 functions. The first one is r squared, and the second one is r over the square root of 4 plus r squared. This way, we have it in an integration by parts friendly form. So we are going to let u equal to r squared, and let dv equal to r over the square root of 4 plus r squared. Next, we take the derivative of u with respect to r, and obtain the following. Then we solve for du as follows. Next, we find v by integrating r over the square root of 4 plus r squared. In order to accomplish this, we need to use u substitution. The only problem is, since we are already using the variable u for integration by parts, I will use u sub s to distinguish it from u that is associated with integration by parts. This is a u that we are using for u substitution. So we're going to let u sub s equal to 4 plus r squared. Next step is to take the derivative of u sub s with respect to r and solve for r dr as follows. So substituting these expressions and simplifying, we obtain the following integral. Taking the integral of u sub s to the power of negative 1/2 yields the following. Then we replace u sub s with the original function, in this case 4 plus r squared, and simplify. So now we have found our v. Next step is to substitute u, v, and du into the integration by parts formula, as follows. Once we have simplified, we need to find the integral of r times the square root of 4 plus r squared dr. Notice that this integral requires u substitution as well. We let u sub s equal 4 plus r squared. Then we find the derivative of u with respect to r, and obtain the following. Next, we solve for r dr, and simplify the expression. Doing that, we obtain the following integral in terms of u sub s. Once we find the integral, we need to evaluate it. the expression in the left bracket will be evaluated from 0 to 1, while the integral in the right requires a change in its limits of integration. So substituting 0 into our u sub s expression that we use to substitute the 4 plus r squared term, we have that 0 is equivalent to 4, and 1 is equivalent to 5. Now we evaluate this integral from 4 to 5. Doing that, we have the following. The terms in the first bracket reduces to the square root of 5, and the terms in the second bracket reduces to 0. The terms in the third bracket reduces to the following expressions, and the terms in the fourth bracket reduces as follows. Next, we factor out a square root of 5 from the first and second terms, as follows. And we continue simplifying the third term. Cleaning up the first term, we have that the integral is equal to negative 7/3 times the square root of 5 plus 16 over 3. More challenging integrals will require you to use multiple integration techniques. Keep in mind that at this point, you should be familiar with u substitution and integration by parts. Alright, let's try the final example. Evaluate the integral from 0 to 1/2 of inverse cosine of x dx. In this problem, notice that we have only one function, the arc cosine of x, also known as inverse cosine of x. At this point, we have no idea how to find the integral of inverse cosine, but we do know how to take its derivative. So we are actually going to use integration by parts. We start by letting u equal to inverse cosine of x, and let dv equal to dx. Remember, you can think of dv as 1 times dx. Having selected our u, we take its derivative, which is equal to negative 1 over the square root of 1 minus x squared. If you forgot how to take the derivative of arc cosine of x, I advise you to check the video titled Derivatives of Inverse Trigonometric Functions in the Calculus 1 section. Alright, having done that, we solve for du. Next, we take the integral of dv to find v, which is equal to x. Now that we have all the required functions, we substitute them into the integration by parts formula. Doing that, we have the following. Now, in order to evaluate the resulting integral, we actually need to use u substitution. If we let u sub s equal the expression under the square root and take its derivative, we would obtain negative 2x. Notice that the variable x also appears in the original integral. This is a telltale sign that u substitution is the way to go. So now, taking the derivative of u sub s and solving for x dx, we obtain the following. Next, we carry on the substitution and obtain the following. The next step is to change the limit of integrations. So using the expression we used to carry out the substitution, we see that 0 is equivalent to 1, and 1/2 is equivalent to 3/4. Notice that the lower limit is greater than the upper limit. We can fix this by reversing the limits of integration and multiplying the integral by a negative number. Recall that the integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx. So in doing that, we have the following. The terms in the first bracket are going to be evaluated from 0 to 1/2, and the terms in the second bracket are going to be evaluated from 3/4 to 1. Substituting the limits, we have the following. The terms in the first bracket signifies to 1/2 times pi over 3. Remember, the inverse cosine spits out an angle and is restricted to quadrants 1 and 2 in the unit circle. The terms in the second bracket is just equal to 0. The term in the third bracket signifies to 1, and the term in the fourth bracket signifies to root 3 over 2. Finally, we simplify the expression and obtain the following. We can also factor out 1/6 from all three terms, which results in the following expression. 1/6 times the quantity pi plus 6 minus 3 times the square root of 3. Alright, and there you have it. That's integration by parts in a nutshell. Keep vigilant of integrals that require the use of both integration by parts and u substitution. In the next series of videos, we will go over how to take integrals that contain certain combinations of trigonometric functions.